And here's my implementation of twiddle. This is a routine that you can keep this way for many, many different applications. All it requires is a way to evaluate something that depends on the parameters and gives you a single error that you'd like to minimize. We have 3 parameters in total. I set the parameters themselves to 0, but the deltas to 1. And it's just a counter, it's unimportant. If the sum of dparams is still larger than our tolerance, which we initialize with 0.001, then I go through all the parameters sequentially. I increment it by dparams, find out what the error is. If the error is better than our best error, which I initialized with the initial error, then I keep the best error and I even increment dparams. Otherwise, I try the other direction. Run, find out the error. If that succeeds, I keep it, I increment dparams. And here's my last case. I didn't succeed, so I'm going to set it back to the old parameter vector and decrease my dparams by 0.9. I increase my counter. Here's my little printout command for debugging. And I return the parameter vector. So let me comment out the print vectors over here and play with this a little more. If I run twiddle, compute the best parameters, and then calculate the error using these parameters, and print out the parameters along with the error, I get a parameter vector, and I get an error that's basically 0. Now let's switch off the integral term. And I can do this with a little trick. I just set dparams number 2, which is the final one, to 0.0, as if I already learned the integral term. When I run this, I get a 0 integral term, but an error that's somewhat larger than the final error that I desired. And that's because the integral term is really required to drive the error down to 0. Let's also remove the d term and see what happens. And the result is a really large error of 0.55. That large error sustains even if I remove the robot drift by commenting it out. We still get an error of 0.10 if we just have a proportional controller, whereas if I add in the differential parameter again by removing the dparam1 command, the 0.103 goes down to 5.7 to the minus 11, which is practically 0. So you can see the importance of the d term for driving the error down to 0 in the case without drift, and for the integral term in cases for robots with a systematic bias. We play a little bit more with this code for the homework assignment, but this is it for now.